السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, today we will continue talking about evaluation functions. We start to talk about them towards the end of the middle of the last lecture, and I think that was the last thing we discussed on and we said that we have to test the evaluation function in multiple scenarios to make sure that it will give us values that will reflect our understanding of the problem. Let me show you now, and we also discussed the depth limited search, right? And that's why actually we use the evaluation function. When we use depth limited search, we limit the depth of the tree that we explore to a specific depth to save time, of course. And when we do that, we'll have to stop at non-terminal nodes. We know that at non-terminal nodes we don't have exact utilities, but instead we will use an evaluation function that will give us an approximated value at these non-terminal nodes. From these approximated values, we'll go up and do minimax as usual. Now let's see the effect of the depth limited search on the decisions that we will make. So we'll start with a situation. It's different from the usual situations that we discussed in the way that we are now at the side of the ghosts. So let's think about being the ghosts ourselves and see how the ghosts actually will behave. So here the goal of the ghost is to kill Pacman. Okay, so you will see that the two ghosts will because we will be using a depth limited search, they will use the evaluation function, and the evaluation function is typically how far we are from Pacman. So as we move closer to Pacman, of course the value will increase because that's the goal of the ghost. So we'll see the effect of that when we have depth limited search, when we are short-sighted in terms of the future, when we don't expand the entire tree to see the end of the game. What will happen? What will happen initially, and what will happen when we actually get closer to the end of the game? So let's see what will happen, and then we'll explain that behavior after that. Okay, so you see the two ghosts are kind of moving together, but what happened at some point, they are not. So up to this, and if we go back, okay, so here they are moving together, okay, in the beginning they are moving together. Why is that? Because they are using the same exact strategy, okay, the same exact strategy, but with limited depth. When we have just depth of 2 or 3, getting closer to Pacman is the best we can do. But at some point, this depth 2 or 3 will include the end of the game, so we can see what is the best to end the game. Okay, so at some point you will see that they will move apart so that they will surround Pacman and kill him. That was not the strategy from the beginning, because the strategy from the beginning was limited by the depth of the tree that we are exploring. So now, at that situation, they are very close to the end of the game. So the expansion of the tree now with the limited depth might show us the ghosts now, might show us the end of the game. And if that's the case, then our decisions will be optimal because we see how we can end the game. Before we couldn't see. So the best we could do is to get closer to Pacman. So if we continue from that point, you will see that, and up to that point, still we don't see the end of the game. Sorry. Sometimes that's really hard to control. Okay, so we are here. Yes, so they started actually to move apart. So see that? Okay. So they move apart now and surround Pacman until they kill him. Okay, so the behavior changed the behavior was kind of naive in the beginning because we don't see the end of the game. As we move forward, the limited depth that we have will allow us, of course, towards the very end of the game, to see the end of the game and thus make better decisions. So that happened here. Now another situation, which is kind of zoomed in more than the previous one. So in that situation, okay, so the board of the game here is limited. Okay, so that means that maybe the depth, the limited depth that we have, will be enough from the beginning to make optimal decisions. So we'll see what will happen in that situation. Okay, so you saw what happened here. Again, okay, so they coordinated from the very beginning. Okay, why is that? Why that happened here? The kind of coordination that one go in the opposite direction so that they surround Pacman. It happened here because the scenario was limited. I mean, they could, even with their limited depth, they could see the end of the game very easily within the depth that is allowed. Okay, so they made this kind of coordination. Of course, there's no real coordination here. The coordination came just because of the strategies that they are doing. They can see the future, they can expand the tree up to the end of the game, so they made optimal decisions together. Okay, it happened that it looked like coordination, but actually there is no coordination. Any question about these two examples? Is the difference clear, and when the behavior changes clear? When and why? Is it clear? Okay. Okay, good. So we'll continue then. Here are some notes about depth limited search. Of course, we said that evaluation functions are always imperfect. Okay, so we cannot expect that the evaluation function will give us exactly the exact value. Otherwise, it would be the terminal nodes. As we go deep in the tree, okay, as we go deep in the tree, we will be very close to the terminal nodes, right? So the effect of the evaluation function will not be as important as, or the quality of the evaluation function will not be as important as the quality of the evaluation function if we are close to the root of the tree. And let me show you that by an example. Let's say that this is the entire tree, okay, and these are the terminal nodes, okay, and let's say that we are here. Our depth is limited to here. So that means that the values of the non-terminal nodes here will be evaluated by, or will be approximated by, an evaluation function. Now, the evaluation function, the effect or the importance of the quality of the evaluation function will be very high, right? Because it tries to approximate huge part of the tree, okay? And it will be, if the decision was bad, if the the approximated values are bad, I will make very bad decisions very early, okay? But if the depth is here, if the evaluation function will be just used here, we are very close to the terminal nodes, which means that we are very close to the end of the game. So whatever value that will be approximated here will not make a big impact on the decisions that we will make by the root of the game, or now. Of course, now means at the root of the search tree. Okay, so the quality of the evaluation function here will be much more important than here. Okay, and that's the point that we are talking about here. The evaluation function will be will not matter much if we are if we are very low in terms of the depth of the tree. If you are very high, then of course this is approximating a huge part of the tree, and thus the quality of the evaluation function will be of a high importance. Another point is that when we compute the evaluation function, if it has so many features, remember last time when we talked about weighted average of features, when we talked about chess and as an example of an evaluation function, if we have so many features and these features are complex to compute, we might get a better estimation of the value of that node, but that might take more time. So there is a trade-off between the complexity of the features and the complexity of the and the time, okay, and of course the quality of the estimated values. Yani if the features are complex to compute, we might get better values, but on the other hand we will spend more time. So that's the trade-off here. We have to consider that when we design the evaluation function. Same thing exactly we said when we talked about the design of heuristics in A-star search. Any question about these nodes before we move on? Because now we will have to show another example of limited depth, but I will show you two examples. One, we have very limited depth of 2, and the other one we have depth of 10. So let me show you this example first. So that's a situation maybe that we didn't see before for Pacman. So Pacman has to go and get this food item, and we have two ghosts here. Okay, so if we don't have, if we are in this situation, okay, if you are in this situation now, if you are Pacman, what would you do? Any thoughts? What's the best you can do here to get to this food item? What is the strategy? What is the idea? How would you do? You do it. Faisal, can you pick up the mic, if possible? Yes. But remember that the other ghosts are also optimal. Then they are trying to kill him. Okay. Okay, type. Let's see what will happen here with limited depth of 2. So Faisal said that I will go down and then go right or left. Okay, maybe based on what the ghost will do, hoping that the ghost will go to the other direction. Hope it won't take much time. Okay, so he went down as we expected, then left, but the ghost go left also. Okay, when he tried to go back, because we have limited depth here, he was killed. Okay, so he was surrounded by the two ghosts in this case. Okay, so maybe that was the best he can do with this limited depth. He has to go somewhere, some direction, but the ghost also is playing against him, right? The two ghosts. So whenever the Pacman will go to the right, the ghosts also will move towards him. So that's what happened when we have limited depth. Pacman can only see 2 movements in the future. Type. If I have more depth, now I have 10, depth of 10. Okay, depth of 10. Before we get to depth of 10, let me also explain something here. So you see here, okay, although we have limited depth here, but the ghosts can at some point can see the end of the game. Okay, at some point the ghosts can see the end of the game and surround Pacman. Okay, now with limited depth of 10 now. Okay, so Pacman can think of 10 movements in the future before making any decision. What would be the strategy of Pacman in this case with the same scenario? I mean, the same setup or the same start of the game. What could be a better action? Anyone other than Faisal? Anyone wants to try? Okay, Mustafa. Wa alaikum salam wa rahmatullahi wa barakatuh, Mustafa. How are you? He has to go down, right? Before left or right. You mean go down first and then go left? But that's the same like the previous one. Okay, why is that? Okay. So طيب. Okay, let's see what will happen and then we will explain it together. Okay, thanks Mustafa. Okay, so what happens here? You see, Pacman went to the opposite direction that we didn't expect. Pacman went up, not down. Knowing that now the depth is 10, why Pacman moved up instead of down? Yusuf? Wa alaikum salam wa barakatuh. But now he has more depth, Yusuf. Yani you saw last time he had limited depth of 2 and he survived for some time. You think that now there is no way to survive, so he will just go up and suicide. Type. Okay, so that's what you think. Anybody else? Any other thoughts? Okay, the other Mustafa Gindi. Okay, what do you mean by wait here? How can he wait? He has to move. لا، ما it's turns مصطفى، يعني ما فيش حاجه اسمها انا مش هلعب خلاص. I have to and I have to move. Okay, so the very good, very good. Okay, so yes, I'm with you. So I got your idea. You want Pacman to wait a little bit, and correct me if I'm wrong. I think that what you are saying is that Pacman should wait a little bit until he sees where the ghosts will go, and then go to the other direction. Is that what you mean? Okay, now how can he do that? He cannot just wait. Yani there's no movement saying wait. It has to be up, down, left, right. Okay. Okay, it doesn't seem that you got my point. If I agree with you that Pacman should wait, but there's no way to stay in the same position in that game. So how can I simulate waiting here? The way to simulate waiting here is to do reverse actions, to go up and then down, which means that I waited for 2 movements, and then in these 2 movements I will see how the other ghost will go, and I go to the other direction. Okay, so let's continue the game here to see what I mean. So Pacman here went up, although that means that he is close to the ghost, right? And by all means, this is very risky. but Pacman can see 10 movements, and he knows that doesn't mean that he will be killed. Maybe 10 movements, by the way, in this small board might mean that I see the end of the game, and I can explore the entire search tree until I see all movements that will get me to the end of the game. That means that I can do optimal decisions now. So Pacman went up. Then let's see what will happen. Okay, hope we will not wait a lot. Yeah, so go down now. And now at that, okay, so let me stop at that point. Okay, so he was up, he went up first, and then moved down. Okay, and now the other ghost moved down after him. Now it's the turn of Pacman. Now Pacman saw that the ghost is going right. Okay, so he will continue. Sorry, that's really bad. Okay, sorry. So he went up again, then down. Now the blue ghost go right. So let's see what Pacman will do now. Okay, so move down one movement. Okay, now it's the turn of the ghost. So the ghost go right. Now Pacman can go left. So that's exactly what we thought we should do. We should wait until we see what the ghosts will do, and then go to the other direction. That's the optimal solution. Pacman was able to do that, and of course, if we continue, Pacman will move around and get the dot. Pacman was able to think that way because he can see in the future deep enough until he gets to the end of the game. So he has in his plans a way to get the best solution. So he was able to, of course, there's no thinking here, it's just planning. Okay, he seemed that he waited for a little bit until seeing where the ghosts will go, and then go to the other direction. Okay, that was only being feasible because Pacman can see more in the future, to the time where I can actually see the end of the game. When I see the end of the game, of course, I will make better decisions. If I don't see the end of the game within my limited depth, then I will rely on the evaluation function. If the evaluation function is good enough, I'm fine. If the evaluation function is not good enough, I might not do good decisions in the beginning, and that's what happened last time. Okay, when we had limited depth of 2. I hope that the difference now is clear. Any questions, Mahmoud? Yes, exactly. Yes, with limited depth you have to do replanning because there is an opponent, right? And you might, based on the action of the opponent, you might change with the new depth. You might not change, of course, what you did before, but I mean you might get different decisions than the decisions that you would do if you use the previous tree. So you have to expand the tree again every time. Did I answer your question, Mahmoud? Okay. That's a good point. In the previous lecture, I think what you are referring to was the uncertainty, when there is a chance, when there is randomness. We don't know what the opponent might not be optimal. Okay, so he might be naive or beginner, so he will not always go against me. But here we don't assume that. Here we assume that the ghosts are always enemies, and are actually mastermind. So they are planning against us or against the agent. Okay, So that's the difference. I think you are referring to the situation where we said that there is a chance to survive. When we did the demo for when the Pacman's the optimal scenario was to being killed as early as possible. I think this is what you are referring to, Mahmoud. Yeah, so that's the difference. That's the difference. Here, there is no uncertainty here. Actually, probably this lecture we will talk about uncertainty, inshallah, maybe in 5 or 10 minutes. But in that situation, you are not assuming that there is uncertainty, there is no randomness. No, there is no randomness. The agents are playing as masterminds, which means that they are optimal. They are playing always against Pacman. Okay. Any other questions? Okay, so thinking that way, as you saw, might lead to ideas that you might not expect because you see more in the future. Okay, that reminds me actually when in our daily lives we say, please think deeply about this decision before you make it. Thinking deeply sometimes means that you consider so many possible scenarios. You think ahead in more depth. Okay, of course we say it deep here, and here it's also deep in terms of the search tree. It's kind of, there is a kind of analogy here. Okay, thinking deep sometimes may mean that you consider so many possibilities. If you really consider so many possibilities and you are certain of these possibilities, of course, then you will make better decisions, and that's and optimal decisions. Okay, of course, assuming that your model matches the real world very much, okay, or very accurately. If your model is not what you have in the real world, then you are doing something that will not be optimal in the real world. Okay, and we talked about that, of course, before. Any more questions, or we should move on? I think we have just one last slide in this set, and then we will inshallah start a new set in the rest of the lecture. So this slide is talking about the interaction between the evaluation function and alpha beta pruning. We talked about the order of expansion before, and of course the evaluation function, if it's good enough, can make a big difference if we are able to expand the most promising nodes first. Okay, then that will make alpha beta pruning more efficient. On another on the other side, if the evaluation function give us accurate values, that will also affect the efficiency of alpha beta pruning. Let me show you an example here. Yeah, let's assume that this is a node, main node, okay, and there is a path here from the max node here. Okay, now let's say that this main node has children here, and we are limited to this depth. So that means that we have to do to use the evaluation function at these nodes, although these nodes are not actually terminal nodes. So there are of course here there is a tree, here there is a tree, and so on. But we have to, because we are using depth limited search, we have to stop at some point and use an evaluation function. Now let's say that the value of this node so far is 15, and the value of this node, the actual value, and if we were to expand this subtree, the actual value of this was 5. Okay, without using the evaluation function. So that means that this value will be 5, and that means that we should prune now, right? If you remember that if this value is less than this, then we should stop expanding this node, and we should now prune the rest of the children. Now, what if the evaluation function, because now we are using evaluation function, we might not get this 5, right? We might get another value. Let's say that this value is 25. That means that the 25 will be passed to the main node, and we will not prune. It's not tight enough. Okay, it's not accurate enough. But if this value instead of 25 was 10, it's closer to 5. Still, it's not exactly 5, but it's closer to 5. It's at least tighter than 25. Now, because this will be 10, 10 is less than 15, we will stop. So that means that the evaluation function will of course affect alpha beta pruning. If the evaluation function can give us here a good upper bound, a good tighter upper bound to the main node, that will allow more alpha beta pruning, more pruning. Okay, it will be alpha pruning here. But if it gave us a very high upper bound like this one, 25, that will actually that might not lead to pruning, and that will waste time. So that shows you the effect of the quality of the evaluation function. If the evaluation function is providing an upper bound on the values on the main node, okay, a good upper bounds, and that upper bound is actually lower than the better option that the max node can get, that means that we can do pruning. Okay, otherwise we will not be able to do that pruning. Any question about this? Is it clear? Is it not clear? Alhamdulillah, Mahmoud. Jazakallah kull khair. Okay, good. That means that we are done with this one, and now we'll start new set of slides. So let me share this now with you. Okay, I think you see now the new slides. Okay, so what will we do here? We will discuss what we call Expectimax search. If you remember from previous, in that session, or still we are in session 5, which is adversarial search, but we will talk about a bit different type of search called Expectimax search. Previously, we were talking about Minimax. Okay? In Minimax, we assume that the opponent is always optimal, is always mastermind, is always playing against the agent. Sometimes that's not true. Sometimes the opponent is not optimal. Sometimes there is some randomness, or there is some uncertainty in what the opponent will do. So how can we deal with uncertain outcomes or uncertain decisions that the opponent can do? This is exactly what we will inshallah address in Expectimax search. I think you remember this example, we discussed it before. This is a Minimax search tree, and if you look at it, as we said earlier, this is very tempting, 100, but we will not get this 100 because the value of this is 10, the value of this is 9, so the maximum will be 10. That means that we will go left, and then the opponent will go left or right. So we will never get this 100. When we say we will never get this 100, we are making a big assumption here. What is that assumption? We are assuming that the opponent is optimal. The opponent is rational. The opponent is making the optimal decision against us. So if it happened that we go right, the opponent for sure, which means certainly, will go left, and thus we will get 9 instead of 10 if we move that way. Okay? So that means that in Minimax search, we are always assuming the worst case. And of course, we should assume the worst case, because we are assuming that the opponent is optimal. Okay, and that's the worst opponent we could play against, right? So that's called the worst case. But what if the opponent is actually not optimal? What if there is a chance that the opponent, if we make this decision, the opponent might make this decision and go right here. If that's the case, we will get 100, right? If it's not the case, we will get 9, which is not very far from 10 that we can get going this way. So if we know that, for example, the opponent here has 50-50 chance to make a decision between these two movements. Yani 50% will go right and 50% will go left. Would we still make a decision to go left from here? What do you think? And if there is just 50% here, 50% chance here, what is the best we can do if that's the case? Mahmoud? Yes, so if in the worst case, in that case, we will get 9, but sometimes we will get 100, right? What would we get on average? On average, we might get 100 or 9, right? So the average of 9 and 100 is not 9, it's 54.5. So on average, we will get 54.5. Here on average, we will get 10. And even if it's 50% here also and 50% here, we'll always get 10, right? So the average value here is 10. The average value here is 54.5. So the value here will be 54.5. How did we get 54.5? It's the weighted average of the values here. We'll talk about that formally, inshallah, very soon. But for now, because we have 50-50 chance, we either get 9 or 100. So on average, we'll get 54.5. Now, is it the case actually if we played the game, we will get 54.5? Of course not. Sometimes we will get 9 and sometimes we will get 100. If we played the game so many times, on average, we will get 54.5. That's the meaning of 54.5 here. Actually, 54.5 is not any of these values. But on average, we will get the gain of 54.5 if we play the game multiple times, or so many times. Because this is 50% and this is 50%. Okay? We call this the average case, not the worst case. If we know for sure that the opponent is optimal, then we take this move. Okay? Because that will give us 10, which is better than 9. But if we know that there is a chance that the opponent will make random choices like that, then on average we will have higher gain than 10, which is 54.5. Okay, so the idea here is that uncertain outcomes controlled by chance. We have probabilities here, kind of probabilities, right? We can model that with probabilities. Okay, so it's not always adversary. We are not always, in this case, playing against optimal enemies who are always planning against us. Sometimes they might not. Okay, and that's how we should model this case. Any question about this, about the concept here? Okay. So, as I said, this is the worst case. We are playing against a mastermind who is always playing against us. Here is one of the best cases if you are playing a beginner, or if you are playing an agent who is making sometimes random decisions. So there is a chance to win. And that will be modeled by probabilities, okay, by the chance. So the chance here will be modeled by, of course, as usual, will be modeled by probabilities. So in this case, we instead of using the many triangles here, we use circles, and these circles we call them chance nodes. Okay, chance nodes. Instead of min nodes, we'll have chance nodes. Chance nodes means that the actions here are based on probability. So with that probability, the agent will make this action. With that probability, the agent will make that action. So now it won't be always minimizing, okay? Because he's not optimal. Minimizing for us is maximizing for him, of course. That's if the player is optimal, if the opponent is optimal. But in this case, he is not. Okay, he is just a chance. He's making random choices. Random, of course, based on some probabilities. Questions? Mahmoud, where is Abdurrahman? Abdurrahman is not here today. Hey. What do you mean by we are now optimal? Our agent? Yes, the agent is max. Yes. The agent is optimal. Yes. Okay. Any other questions? Okay. Now, why wouldn't we know the result of an action? Yani, why would we say that this is 0.5 and that's 0.5? Is that realistic? Yani, when can we model the game like that? There are multiple reasons for that. First, maybe this is part of the rule of the game. And we are playing a game where the opponent will roll a die, and based on the value that he will get, he will make an action. We, of course, know many games like that. So in that case, it's based on chance, based on probabilities. Okay? So that's part of the rule of the game. Or maybe the agent himself will respond randomly. It's not based on the rule, but the action of the opponent or the enemy or the ghosts, if you think about Pacman, will have some random behavior. Okay, so in the strategy of the agent himself, he is making at some point random actions with some probabilities. Okay, so that might be part of the behavior or the strategy of the opponent. That's a second reason. A third reason is about the actions that I am taking myself. And the classic example here is the robot. Let's say that we are controlling a robot, so the agent is a robot, and the robot is making decisions of some movements. Some of these movements, when we do a movement, the wheels might slip, and the position will be different than what I expect. So there is a chance that the actions will be different. So there is some randomness here. Okay, so the randomness is now inherent in the actions of the agent. Okay, because of possible failures in real life. So how can I model this? I model this by chance node, by adding a chance model, by adding probabilities into the search tree, as we will see. Okay, now the values will reflect, as we said in the previous slide, the values will reflect average case. That's why we call it Expectimax. You remember expectations in statistics? That's where we got this name, Expectimax, because at the nodes of the opponent, we will compute the expectation, the weighted average of the values. Okay, so we are dealing with average case, which means that this is the value that we will get on average. If we play the game so many times, on average, that's the value that we will get. Okay, this is different than the worst case, which is the case when we run Minimax. That's a summary of the Expectimax search. So we'll compute the average score under the optimal play from our side. So the max nodes will be the same as in Minimax, but the chance nodes will be like min nodes, but the outcome is uncertain. When we have uncertain outcomes, that means that we'll have to compute expected utilities, not exact utilities. Okay, the expected utilities will be weighted average of the children. Weighted average means expectation, if you remember from statistics, and that's why it's called Expectimax. Okay, max is our agent, and the expected behavior, expected case, or the expectations that will be computed will be on the opponent. Let me show you now a demo that we saw before, but now knowing that this is called Minimax and that's called Expectimax. Actually, we discussed that earlier today. Let me show you again this. This is the scenario where Pacman is surrounded by two ghosts. If I know that the ghosts are optimal, then as we said earlier, the best thing we can do is to move to the right and suicide. Okay, so that's if Pacman is using Minimax. Okay, and using Minimax here means that Pacman is assuming that the opponent is optimal. Now, if Pacman knows that the opponent is not optimal, is working by chance, there is some randomness and modeled in the right way, then as we saw before, Pacman might decide to take his chance, and instead of going right to be killed as early as possible, will go left, as we saw before. Okay, sorry. So in this case, Pacman decided to go left. Okay, let's see what will happen. Okay, now the ghost actually moved towards him. It can happen, right? So in that case, because there is a chance, in that case, Pacman will be killed with a score that is lower than suiciding. Now, if we play the game again, that might change. Let's see what will happen. I think that's the second one, I hope. Let's see now what will happen. Yes, in the second case, the ghost was naive and moved far from Pacman. Okay, so that's the kind of randomness we are talking about. It might happen to be the best case. It might happen to be the worst case. Okay, on average, the gain of Pacman was better than the assuming that was better than Minimax. Okay, because in Minimax, it's always the case that the agent is playing against us. Any question about this? Still have 1 minute. So in terms of implementation, if you don't have any questions, in terms of implementation, it's very similar to Minimax, except that now, instead of having to minimize the values, so if this is replacing the min value function, it will be value function, or expectation value function. Here we are computing weighted average. Okay, so we'll get the probability of the successor, and then multiply this probability with the value and add them. Okay, so that's the weighted average instead of the minimization that we were doing in Expectimax. Now, this is another example. If I want to compute the value of this node here, this is a chance node, and I have these probabilities and I have these utilities, then the value here will be computed as follows. Will be computed as weighted average. So I will add up the multiplication of the probability with the utility value. So the value here will be half times 8 plus 1 over 3 times 24 plus 1 over 6 times minus 12. And that will be the value here for the chance node. So this is 4, this is 8, this is minus 2, 4 plus 8 minus 2, this is, I think, 10. Okay, now the value of this node is 10. Notice that this 10 is not any of these values. Okay, because this is just the expected value. We have to stop here because maybe some of you have exams. I also have an exam. So I have to stop here exactly. Inshallah, we'll continue not the next lecture because of the exam, but the lecture after. Please study hard. I wish you, inshallah, great success in the exam. Please make sure that you read the instructions that I sent you about being early to the classroom. Try to read it carefully. What else? Of course, this lecture will not be covered in the exam, so the exam will cover up to the material of the previous lecture, and inshallah we'll continue, we'll pick up from here for the lecture on Tuesday. Now, for the first time this semester, I can say certainly, inshallah, I will see you inshallah on Sunday on the exam, and then inshallah we'll continue after that from Tuesday back the online lectures. See you inshallah on Sunday. Assalamu alaikum wa rahmatullahi wa barakatuh.